Today's topic is memories. The memory of a computer is where the program and data are stored before the calculation begins. So, program and data are stored in the memory before the calculation begins. During a computer run, the control section may store partial answers in the memory. So, memory is therefore one of the most active parts of a computer, storing not only the program and data but processed data as well. A memory is equivalent to thousands of registers, each storing a binary word. The latest generation of computers relies on semiconductor memories because they are less expensive and it is easier to work with them. So one of the memories is ROM, ROM. A read-only memory, ROM. ROM is short form of read-only memory. A read-only memory is the simplest kind of memory. It is equivalent to a group of registers, each permanently storing a word. By applying control signals, we can read the word in any memory location. Binary word in memory is stored in some memory location. Read means that the content of the memory location appear at the output terminals of the ROM. Diode ROM. This figure A shows one way to build a ROM. Each horizontal row is a register or memory location. This is the figure which shows how to build a ROM, read-only memory. Each horizontal row is a register or memory location. We have these 8 horizontal rows from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. These are 8 horizontal rows. Each horizontal row is a register or memory location. It is a register which can store a binary word, or it is a memory location which can store a binary word. The R0 register contains 3 diodes. These are the registers R0, R1, R2, R3 up to R7. These are 8 registers. These are 8 horizontal lines. These 8 horizontal lines are 8 registers. We write them R0, R1, R2, R3 up to R7. These registers, each register represent a memory location and it can store a binary word. Each horizontal row is a register or memory location. It can store a binary word. The R0 register contains 3 diodes. This is the R0 register. It contains 3 PN diodes. Similarly, R1 register contains only 1 diode. R2 contains 3 diodes. R3 contains 2 diodes, and so on. The R0 register has 1 diode. The R0 register contains 3 diodes. See this figure. R0 register contains 3 diodes. And again we write the R0 register has 1 diode. So it is not R0. Second time it is not R0 but it is R1. The R1 register has 1 diode. Look at the figure. R1 register contain 1 diode. So correct here, it is not R0, it is R1 register which has 1 diode, and so on. The output of the ROM is the word. Output of this ROM is obtained here, and it is the word D3, D2, D1, D0. We write it as D. D is a 4-bit word. D3, D2, D1, D0. These are obtained here. D3, D2, D1, D0. In switch position 0, in this figure, this switch is connected between plus 5 volt and the terminal 0. In switch position 0, which is shown in this figure, a high voltage turn on the diodes in the R0 register. If this switch is connected to 0, plus 5 volt high voltage is applied to this R0 register, which contains 3 diodes. A high voltage turn on the diodes in the R0 register. All other diodes are off. So a high voltage appears at D2, D1 and D0. D2, D1 and D0 are connected to these 3 diodes of register R0. So a high voltage appears at D2, D1 and D0. Therefore, the word stored at memory location 0 is D equal to 0, 1, 1, 1. So this is the memory location 0. Switch is connected to 0 and 0 is connected to this horizontal line which we call R0 register, and it contains 3 diodes which are connected to D2, D1 and D0. So these D2, D1 and D0 becomes 1. D3 will be 0. So the word obtained will be the 0111 in R0 register or in R0 memory location. Similarly, we can see that if this switch is connected to 1, then in R1 register we have only one PN diode and it is connected to D3. So D3 will be 1 and D2, D1, D0 are 0 and the stored word will be 1000 and so on. So we see that each memory location or each register R0, R1, R2 will store a certain binary word of 4 bits. As we move the switch to other positions, we will read the contents of the other memory locations which are shown in table B. This is the table which shows the contents of different registers R0, R1, R2, R3 up to R7. This 0, 1, 2, 3, 4 which we write with capital R is the address of memory location, and at this address what is the word which is stored at this memory location, it is shown in third column. In third column we have the stored word. In second column we have the address of the memory location 0, 1, 2, 3, 4 up to 7, it is the address, and in last column we have the binary word which are stored in these memory locations. Addresses. The address and contents of a memory location are two different things. If we have a memory location, it will have certain address and it have certain content in it. So memory location, address of memory location is different and its content is different. The address and contents of a memory location are two different things. For example, if we see this table, the address of memory location or register R0 is 0 and the stored word is 0111. Similarly, address of register R1 is 1 and the word stored in it is 1000 and so on. The address and contents of a memory location are two different things. The address of a memory location is the same as the subscript of the register storing the word. Subscript of register R0 is 0, which is its address. Subscript of register R1 is 1, which is its address. And these are the contents. These are different. Register R0 has an address 0 and its contents are 0111. Register R1 has an address 1 and its contents are 1000 and so on. on-chip decoding. Rather than switch, select the memory location IC manufacturers use on-chip decoding. It is illustrated in figure C. In this figure, we have used this switch. Switch is connected to 0, 1, 2, 3 and so on. And then we see the binary word stored in different memory locations. But these switches are generally not used and on-chip decoding is used. Rather than switch, select the memory location IC manufacturers use on-chip decoding. It is illustrated in figure C. On-chip decoding is shown in this figure. This also has 8 horizontal lines. These are 8 registers R0, R1, R2, R3 up to R7. And in place of switches, we have these lines A2, A1, A0 and their complements A2 bar, A1 bar, A0 bar. Complements are obtained by using NOT gates. These 3 lines for A2, A1, A0 and 3 lines for their complements A2 bar, A1 bar and A0 bar are used for address of memory location. The 3 input pins A2, A1 and A0 supply the binary address of the stored word. Then a 1 of 8 decoder produces a high output to one of the registers. If we have 3 lines, 3 pins, then we have 2 to the power 3, that is 8 registers from R0 to R7. If we have only 2 pins, A1 and A0, then we will have 2 to the power 2 registers, that are 4 registers. If we have n lines, then we will have 2 to the power n registers. The 3 input pins A2, A1 and A0 supply the binary address of the stored word. First binary word, first address is 000. A2 is 0, A1 is 0 and A0 is 0. Then this R0 is connected to their complements A2 bar, A1 bar and A0 bar, which are 111. So if we start the address from 000, next address will be 001. Next address is 010, which are binary equivalent of decimal numbers 0, 1, 2, 3, 4, 5 up to 8. We have 8 such combinations for these 3 pins A2, A1, A0 from 0, 0, 0 to 1, 1, 1. So the first address is 0, 0, 0. So this AND gate of register R0, the inputs of this AND gate are A2 bar, A1 bar and A0 bar. Next address is 0, 0, 1, which is equivalent to 1. So if we have 0, 0, 1, then A2 is 0, A1 is 0 and A0 is 1. So the register R1, the inputs of register R1 will be A2 bar, A1 bar and A0, because A0 is 1. So we have A0 and the other two pins A2 and A1 are 0, 0. So we use their complements. And a similar manner we can see what will be the inputs of different AND gates of different registers. For example, if address equal to A2, A1, A0 is 100, if it is the address, the 1 of 8 decoder produces a high output to register R4. 100, its decimal equivalent is 4. So if we have address 100, A2 is 1, A1 is 0 and A0 is 0, then since it is equivalent to 4, so we look at this R4 register. Inputs of this AND gate of R4 registers are A2, A1 bar, A0 bar. A2 is 1, so input will be A2 because it is 1, and since A1 and A0 are 0, 0, so in its input we have A1 bar and A0 bar. So in R4, look at the AND gate of this R4 register and see the inputs of this AND gate. These are A2, A1 bar and A0 bar. So if we have address 100, the 1 of 8 decoder produces a high output to register R4 and the ROM output is D equal to 0, 1, 1, 0. Because in R4 we have these two diodes and these are on, and these two diodes are connected to D2 and D1. So D2 is 1 and D1 is 1 and the stored word will be 0, 1, 1, 0 in R4. So if we have address A2, A1, A0 as 100, the content in this memory location is this word D, which is 0, 1, 1, 0. If we change the address word to address 110, then 110, its decimal equivalent is 6, we will read the contents of memory location 6, and content of memory location 6, look at this R6. It has two diodes which are connected to D1 and D0. So D1 is 1, D0 is 1, other D3, D2 are 0, 0. So content word is 0011. Circuit of figure C is a 32-bit ROM organized as 8 words of 8 bits each. 8 words because we have 8 registers from R0 to R7, and each register is storing a binary word of 4 bit each. It is not 8 bit each, it is 4 bits each. We have 8 words because we have 8 registers, and each word is 4 bits each. We have 4-bit word. So 8 registers and 4 bits, we call it 32-bit ROM. 8 into 4-bit ROM. So this circuit of figure C is a 32-bit ROM. 32 bits mean 8 into 4. As 8 words of 4 bits each. Correct this. This is 8 words of 4 bits each. With on-chip decoding, n address lines can select 2 to the power n memory locations. If we have 3 lines, memory locations are 2 to the power 3, that's are 8. So we have from R0 to R7 8 memory locations. If we have n lines, then we will have 2 to the power n memory locations. EEPROMs and EEPROMs. With a ROM, we have to send a list of data to be stored in the different memory locations to the manufacturer, who then produces a mask used in mass production of ROMs. Mask is a photographic template of the circuit. So with a ROM, we have to send a list of data to be stored in the different memory locations to the manufacturer, and manufacturer then produces a mask which is photographic template of the circuit which is used in mass production of ROMs. PROMs. PROMs is programmable ROM. A programmable ROM, PROM, is different. It allows the user to store the data. In ROM, user cannot store the data. It is the manufacturer which store the data. In PROM, programmable ROM, it allows the user to store the data. With an instrument called PROM programmer, the user can burn the program and data. Once this has been done, the programming is permanent and the stored contents cannot be erased. Next is erasable programmable ROM, EEPROM. E for erasable, P for programmable. Erasable programmable ROM, EEPROM. Erasable programmable ROM, which is EEPROM, it uses MOSFETs. Data is stored with PROM programmer. Later, data can be erased with ultraviolet light. The light passes through a window in the IC package to the chip, where it releases stored charges which erases the data. So, in erasable programmable ROM, we have programmable ROM, and to erase, we will use ultraviolet light. By using ultraviolet light, we can erase the data. The EEPROM is ultraviolet light erasable and electrically programmable. EEPROM is helpful in design and development. The user can erase and store until the program and data are perfected. Then the program and data can be sent to an IC manufacturer who makes a ROM mask for mass production. EEPROM. It is the electrically erasable programmable read-only memory. Electrically erasable programmable ROM. In erasable programmable ROM, EEPROM, we use ultraviolet light to erase the data. In this EEPROM, it is electrically erasable programmable ROM. It does not require ultraviolet light to be erased. It can be completely erased or have certain byte changed using electrical pulses. Individual bytes or any number of bytes can be changed using a programmer designed for use with EEPROMs. Access time. The access time of a memory is the time it takes to read a stored word after applying address bit. If we apply some address bit, then some time is needed to read the content of memory location. This time is known as access time. So access time of a memory is the time it takes to read a store word after applying address bits. Bipolar memories have faster access time than MOS memories. 3-state memories. By adding 3-state switches to the data lines of a memory, we can get a 3-state output. Figure B shows a 16384-bit ROM organized as 2048 words of 8 bits each. These are the address lines A10, A9, A8 up to A0. So from A0 to A10, these are 11 address lines. So memory locations will be 2 to the power 11, and 2 to the power 11 is 2048, and in each of these 2048 memory locations, each of these memory locations store a word of 8 bit each. These are the 8-bit words: D7, D6, D5, D4, D3, D2, D1, D0. This is the 8-bit word. And these are the address lines. Since these lines are 11, so we have 2 to the power 11 memory locations, and each memory location will store a 8-bit word. So we call this memory as 2048 into 8, that is 16384-bit ROM. So it is a 16384 bit. 16384 comes from 2048 into 8, and 2048 comes from 2 to the power 11 because we have 11 address lines. So this is ROM, and we are using here these 3 state switches. These are the 3 state switches. When enable is high, it is 1, then this will show the word stored in this ROM. It has 11 address lines and 8 data lines. A low enable opens all switches and floats the output lines. If enable is low, output lines are floating. A high enable allows the addressed word to reach the final output. Non-volatile memory. ROMs, PROMs and EEPROMs are non-volatile memories because they retain the stored data even when the power to the device is shut off. So such memories are known as non-volatile memories, which retain the stored word data even when the power to the device is shut off. If we shut off the power of the device, even then the data remains stored in that device. Such memories are known as non-volatile memories. ROMs, PROMs, EEPROMs are such non-volatile memories.